Drop a cup, it falls. Step on a scale, it shows your weight. Look at the moon, it stays locked around Earth. For centuries, this seemed simple. Mass pulls on mass. Earth pulls the cup. The sun pulls the planets. Gravity is an invisible force reaching across space. Newton wrote the equation, and it worked so well that scientists used it to predict planets, tides, comets, and spacecraft paths. But Einstein saw something hidden inside this success, a problem so deep that it changed the meaning of gravity itself. Because the falling cup may not be the object experiencing a force. It may be the only object in the room that is truly free, and you, standing still on the ground, may be the one being pushed away from your natural path. That sounds impossible, but it is the doorway into Einstein's universe. To understand why mass creates gravity, we have to abandon the idea of gravity as an invisible pull. We have to ask what Newton's equation could calculate perfectly, but never explain. How does gravity cross empty space? Why does every object fall the same way? Why did Mercury refuse to obey Newton completely? And why did Einstein believe the answer was not a force at all, but something far stranger hidden in the structure of space and time? This is the story of how gravity stopped being a pull and became the shape of reality. To understand why Einstein changed gravity forever, we first have to understand why Newton was so hard to challenge. Newton's gravity was not a weak idea. It was one of the greatest successes in the history of science. Before Newton, the falling apple and the orbiting moon seemed like different mysteries. One belonged to Earth, the other belonged to the heavens. Newton united them. He said the apple falls toward Earth, and the moon also falls toward Earth. The only reason the moon does not crash into the ground is because it is moving sideways so fast that it keeps missing. It is falling forever around Earth. That idea was breathtaking. Suddenly, the motion of planets, comets, tides, moons, and falling objects could be described with one law. Every object with mass attracts every other object with mass. Greater mass means stronger attraction. Greater distance means weaker attraction. Simple, clean, powerful. And for more than 200 years, it worked. Newton's equation could predict where the moon would be, how tides would rise, how planets would move, and how comets would return. It was not just a beautiful theory. It was a working machine for understanding the sky. Its greatest triumph came in the 1800s. Astronomers noticed that Uranus was not moving exactly as Newton's law predicted. Its orbit was slightly off. Instead of assuming Newton was wrong, they asked a different question. What if another planet, unseen by any telescope, was pulling on Uranus? Mathematicians calculated where that hidden planet would have to be. Then astronomers looked in that region of the sky, and they found Neptune. A planet had been discovered with mathematics before it was discovered with eyes. That is why Newton's gravity felt almost untouchable. If an equation can reveal an unseen world, you do not abandon it easily. But Einstein noticed something dangerous. Newton's equation told you how strong gravity was. It did not tell you how gravity worked. It described the effect, but not the mechanism. Imagine the sun and Earth separated by empty space. According to Newton, the sun pulls Earth. But what carries that pull? There is no rope, no chain, no rod, no visible messenger crossing the vacuum. Earth is not touching the sun. So how does Earth know where the sun is? Newton himself knew this was a problem. The idea that one body could act on another through empty space with nothing in between disturbed him deeply. But the equation worked, so the world kept using it. For most scientists, that was enough. For Einstein, it was not. Because by 1905, Einstein had already changed physics once. Special relativity showed that nothing can travel faster than light, not matter, not energy, not information, not influence. The speed of light was not just the speed of brightness, it was the speed limit of reality, and that created a crisis for Newton's gravity. In Newton's picture, gravity acts instantly. If the sun suddenly disappeared, Earth would immediately lose its pull and fly off in a straight line. But Einstein's universe does not allow instant communication. The news that the sun had vanished could not reach Earth faster than light. It would take about 8 minutes, so gravity could not be an immediate invisible tug. There had to be something else. And then there was Mercury. Mercury, the planet closest to the sun, was the perfect test. It moves through the strongest gravitational region in the solar system. Its orbit should be where Newton's law is most exposed. Mercury does not trace the same ellipse forever. Its orbit slowly rotates around the sun. Most of this motion can be explained by the pull of the other planets, but not all of it. A tiny difference remained, about 43 arc-seconds per century. That sounds almost nothing. But in physics, a tiny error that refuses to disappear is not nothing. It is a warning. Astronomers tried to explain it the same way they had explained Uranus. Maybe another hidden planet was pulling on Mercury. They named this possible planet Vulcan. They searched for it. They waited for eclipses. They watched near the sun, but Vulcan never appeared. Because the problem was not a missing planet, the problem was the old picture of gravity. So Einstein had two cracks in Newton's universe. Gravity could not act instantly, and Mercury was not obeying Newton completely. But Einstein's real breakthrough did not begin with a telescope. It began inside an imaginary elevator. Picture yourself sealed inside a small elevator with no windows. You cannot see outside. You do not know whether you are on Earth, in space, or somewhere between the stars. If the elevator is resting on Earth, you feel weight. Your feet press against the floor. Drop a coin, and it falls. Now imagine the same elevator, far out in deep space, away from planets and stars. At first, everything floats, but then a rocket attached to the elevator begins accelerating upward. Suddenly, your feet press against the floor. A dropped coin falls. A scale shows your weight. Everything inside behaves exactly as it would on Earth. Einstein asked the question that changed gravity. Can you tell the difference? If the elevator is small enough and the measurements are local enough, can any experiment inside reveal whether you are being pulled by gravity or accelerated by a rocket? Einstein's answer was no. The two situations are physically equivalent. This was the equivalence principle. He later called it the happiest thought of his life, and hidden inside it was a revolution. Because if acceleration and gravity can imitate each other perfectly, then gravity may not be a normal force at all. Maybe our everyday picture is backwards. When you stand on Earth, you think you are at rest. When a cup falls, you think the cup is being forced downward. But Einstein asked a stranger question. What if the cup is the free object? What if the falling cup is following its natural path? And what if you, standing still on the floor, are the one being forced away from your natural path? At first, this sounds like a trick, but think about what you actually feel. You do not feel an invisible hand pulling every atom of your body downward. You feel pressure. Your feet press into the floor. The chair presses against your back. The ground stops you from falling. That pressure is what you call weight. Einstein's insight was that weight is not the direct feeling of gravity pulling you down. Weight is the feeling of something preventing you from falling freely. A falling object feels weightless. An astronaut in orbit feels weightless. A person inside a freely falling elevator would feel weightless. Not because gravity has disappeared, but because everything inside is moving together along the same natural path. That is the first great reversal. Free fall is not forced motion. Free fall is natural motion. Standing still on the ground requires force. The floor is pushing you upward, stopping you from following the path you would take if nothing held you back. But this created a deeper question. If falling objects are not being pulled by a force, then what path are they following? Einstein's answer was geometry. He began to imagine space and time not as a silent stage where objects move, but as something active, something flexible, something shaped by mass and energy. In ordinary life, we know that the shortest path depends on geometry. On a flat sheet of paper, the straightest route between 2 points is a straight line. But on the curved surface of Earth, the straightest route between two distant cities may look curved on a flat map. A plane flying from New York to London bends northward on the map, but on the globe, it follows the natural route. The path looks curved only because the surface is curved. Einstein applied this idea to the universe itself. Objects moving freely follow the straightest possible paths through space-time. These paths are called geodesics. Near Earth, space-time is not flat. Earth's mass changes its geometry. So when a cup is released, it follows the straightest available path through that curved geometry. To us, that path looks like falling. To the cup, there is no force. It is simply free. This was Einstein's new picture of gravity. Not invisible threads, not instant pulling, not action at a distance, but motion through curved space-time. And this explains something Newton had left mysterious for centuries. Why does everything fall at the same rate? In Newton's theory, heavier objects feel a stronger gravitational pull, but they also have more inertia. The two effects cancel. That gives the right answer, but it leaves a suspicious coincidence. Why should gravitational mass and inertial mass be exactly equal? In Einstein's theory, this equality is not a coincidence. If gravity is geometry, then every freely falling object follows the same space-time path, regardless of its mass or material. A wooden ball and a lead ball fall together because they are not choosing paths based on what they are made of. They are following the same geometry. That is why the equivalence principle was so powerful. It turned a strange coincidence into a necessary result. But Einstein was not finished. If gravity is space-time geometry, then it should affect more than falling objects. It should affect light. It should affect clocks. It should affect the orbit of Mercury. It should create predictions Newton could never produce. And that is exactly what happened. The tiny error in Mercury's orbit dropped out of Einstein's equations naturally. No Vulcan, no hidden planet, no patch, just curved space-time near the sun. And then came an even more dramatic prediction. If light follows space-time geometry, then light passing near the sun should bend. Not because light is being pulled like a stone, but because the road it travels through is curved. During the 1919 solar eclipse, astronomers measured the apparent positions of stars near the sun. The observations supported Einstein's predictions strongly enough to make him famous around the world, though later scientists would refine the evidence with far better measurements. Newton's universe had cracked. Einstein's universe had opened. But the most shocking part was still ahead. Because Einstein's theory did not only say that space bends, it said time is involved too. Clocks near massive objects do not tick at exactly the same rate as clocks farther away. For slow-moving objects near Earth, differences in the flow of time form a major part of the space-time geometry we experience as gravity. This is where gravity becomes stranger than a pull. It is not only about where things move, it is about how time itself flows. And once time can bend, the question becomes terrifying. What happens when mass becomes so concentrated that space-time curves beyond escape? What happens when the straightest paths all begin to lead inward? Einstein had replaced gravity with geometry, but now that geometry was about to predict monsters, Einstein had replaced a force with geometry. But now that geometry began making predictions so strange that even Einstein himself was not always comfortable with where they led. Because if Earth bends space-time slightly and the sun bends it more strongly, then what happens when mass becomes extreme? What happens when a massive star dies? A star is a balance between two enemies. Gravity tries to crush it inward. The pressure from nuclear fusion pushes outward. For millions or billions of years, the star survives because these two sides are locked in balance. But when the fuel runs out, the outward pressure weakens. The star begins to collapse. For many stars, the collapse stops. But for a star massive enough, nothing known can hold it up forever. The core shrinks, density rises, space-time curves more sharply, and Einstein's equations predict a terrifying possibility, a region where the curvature becomes so extreme that every future path leads inward. This is a black hole. But a black hole is not simply an object with very strong gravity. It is not a cosmic vacuum cleaner. It does not suck in the universe. If the sun were somehow replaced by a black hole of the same mass, Earth would continue orbiting almost the same way. From far away, the total mass would still be the same. The danger appears when you get close. Near a black hole, space-time is curved so severely that escape becomes impossible. The boundary is called the event horizon. It is not a surface you can touch. It is not a wall. It is not a physical shell. It is the point beyond which all future paths point inward. Once something crosses the event horizon, escape is not merely difficult. It is no longer part of the available geometry. Even light cannot leave, not because light is pulled back like a stone, but because there is no outward path for light to follow. The road itself leads only one way. This is why black holes are such a powerful test of Einstein's idea. Newton's gravity says force becomes stronger. Einstein's gravity says the structure of space-time itself changes. And in a black hole, that structure becomes a trap. Ironically, Einstein was not eager to accept that nature would actually create such objects. He trusted his equations, but he was cautious about their most extreme consequences. Yet the universe did not ask for permission. Today, we have strong evidence for black holes. We observe stars orbiting invisible massive objects. We see hot gas glowing as it spirals around dark centers. We have images of black hole shadows, and we have detected the ripples created when black holes collide. Those ripples are another prediction of general relativity. If space-time is real geometry and if mass can disturb it, then space-time should not remain perfectly still. It should ripple. Imagine a still pond after a stone falls in. Waves move outward across the surface. Now replace the pond with space-time itself. When enormous masses accelerate, especially two black holes spiraling around each other, they send waves through space-time. These are gravitational waves. Einstein predicted them in 1916. For a century, they were almost impossible to detect because the effect is unbelievably tiny. By the time gravitational waves reach Earth, they stretch and squeeze space by less than the width of a proton across kilometer-scale detectors. It sounds impossible to measure. But in 2015, LIGO detected gravitational waves for the first time. The signal came from two black holes merging more than 1 billion light-years away. For a brief moment, that collision released energy into space-time itself, and Earth felt the faint echo. Humanity had not just seen the universe. We had listened to the universe's geometry move. That moment confirmed something profound. Gravity is not instant. Gravity is not a hidden string. Gravity travels. Space-time responds dynamically. Newton's universe was a stage. Einstein's universe is more like a living fabric, able to bend, stretch, ripple, and collapse. But there is one more layer to the mystery, because general relativity does not only change space, it changes time. Clocks near massive objects tick differently from clocks farther away. This has been measured. It is not science fiction. Atomic clocks at different heights run at slightly different rates. GPS satellites must correct for relativistic time differences, or navigation would drift badly. This means gravity is not just about where objects go. It is also about how time flows. For slow-moving objects near Earth, differences in the flow of time form a major part of the space-time geometry we experience as gravity. That sentence sounds almost unbelievable. The weight of your body, the fall of a cup, the orbit of the moon. These familiar things are connected to the geometry of space-time, including the way time runs differently in different gravitational fields. But we have to be careful. It is not that an object consciously seeks slower time, and it is not that time alone explains all of gravity. The full theory is space-time geometry, space and time together. But near Earth, where objects move slowly compared with light, the difference in clock rates is one of the deepest clues to why gravity feels the way it does. This is why Einstein's theory is so much more than a correction to Newton. Newton gave us a formula. Einstein gave us a new picture of reality. And that picture keeps returning to the same astonishing idea. Matter and energy shape space-time. Freely moving objects follow the straightest possible paths through that shaped space-time. What we call falling is often just that natural motion seen from the outside. What we call weight is the pressure of being prevented from following it. But now we arrive at the deepest question: why? Why does mass bend space-time? Why does energy affect geometry? Why should the presence of matter change the flow of time? Einstein's field equations tell us how to calculate this relationship with extraordinary precision. They connect mass, energy, pressure, and momentum with the curvature of space-time. The equations work. They explain Mercury's orbit. They predict the bending of light. They predict gravitational waves. They allow black holes. They explain why clocks run differently in gravitational fields. But the equations do not fully answer the ultimate why. They describe the relationship. They do not reveal what space-time is made of, or why energy should command geometry in exactly this way. That question may belong to the next great theory, a theory beyond Einstein, a theory of quantum gravity, because at the smallest scales, another theory rules nature: quantum mechanics. Quantum mechanics describes atoms, particles, and probability. General relativity describes stars, galaxies, black holes, and space-time. Both theories are astonishingly successful. But when we try to combine them completely, they resist each other. Inside black holes, and perhaps at the beginning of the universe, gravity becomes extremely strong, and quantum effects cannot be ignored. That is where our current understanding begins to break. Some physicists suspect space-time itself may not be fundamental. Maybe it emerges from something deeper. Quantum information, entanglement, tiny structures beyond direct observation. Something we do not yet have the language to describe. If that is true, then Einstein's curved space-time may be like the surface of an ocean, smooth from far away, but built from something smaller underneath. We do not know, and that uncertainty is not a failure. It is the frontier. Newton asked what force pulls the apple. Einstein asked whether the apple is being pulled at all. The next revolution may ask what space-time itself really is. But until that theory arrives, Einstein's gravity remains one of the most beautiful ideas ever discovered. It takes the most ordinary experience in life, falling, and reveals something extraordinary behind it. The cup slips from your hand, it falls. But in Einstein's view, it is not being dragged by an invisible rope. It is following a natural path through curved space-time. The moon circles Earth, but it is not attached by a hidden chain. It is moving through the geometry created by Earth's mass. You stand on the ground and feel weight. But that feeling is not gravity itself. It is resistance. The ground is pushing you away from the path you would naturally follow if nothing held you up. This is the reversal that changes everything. Gravity is not what you feel when something pulls you down. Gravity is what you follow when nothing stops you, and that is why Einstein's idea is so powerful. It does not merely answer an old question, it changes the question. The universe is not a machine filled with invisible ropes. It is a geometry where matter, energy, space, and time are woven together. A planet moves because space-time has a shape. A beam of light bends because its road is curved. A black hole traps light because all future roads lead inward. A gravitational wave passes because space-time itself can tremble. Newton showed that gravity obeys a law. Einstein showed that the law comes from geometry. And perhaps the next Einstein will show where that geometry comes from. But for now, the deepest truth we have is still simple enough to say in one line: matter tells space-time how to curve. Space-time tells matter how to move. If this changed the way you see gravity, subscribe to the channel and comment below. What feels more shocking, that falling is freedom or that standing still means the ground is pushing you away from your natural path?